Thanks, Anne. So I'll be talking about, as you said, optical frequency conversion, which is basically changing the wavelength of light with optimized nanostructures. And this work was done as part of the ARC Center of Excellence for Transformative Meta-Optical Systems, TMOS, at Australian National University. And this work was done with collaborators here, Matthew Parry, Jihua Zhang, and my supervisor, Andrei Sukharukov. So I will go through the brief outline of the talk. We'll start with an introduction to metasurfaces and how they manipulate light. Then enhancing optical nonlinearity, in particular with metasurfaces. Finally, I'll briefly talk about topology optimization and how that has aided a lot of metasurface design in the recent couple years. And then I will show some of the results from this work. So on the right is a picture of a recently kind of published idea of very miniature optical components. And there's a lot of interest in miniaturizing optical components because it is cheaper and just more space efficient for many future applications. So metasurfaces, they are resonators tailored specifically to scatter some property of light. So this could be the momentum, the intensity, or the polarization state. And many people believe that this will revolutionize optical components in the future and really has been enabled by precision nanofabrication techniques developed over decades. And as I said, it will give opportunity for extremely thin and miniaturized optics. So far, they've been used in many applications, such as spectrometry, polarimetry, and meta lenses. And because of these nanoresonators being sub-wavelength in size, the properties can be especially tailored for these applications that would not be present in bulk optical components, for example. On the right is a work demonstrating the polarization selectivity of certain metasurfaces. Other applications include visible achromatic meta lenses with very high NAs, numerical apertures. And they also enable strong light matter interactions, which will lead to even light emitting metasurfaces. All right, so the area that I'm interested in is in nonlinear frequency generation. And the second order case is some frequency generation. There are other higher orders as well. In some frequency generation, the incident waves, there are two, drives a polarization density inside the material, which excites a third wave. And the third wave has a simple relationship to the first two, which is the sum of the frequencies. And so the energy of the exiting photon is just the sum of the energies of the incoming photons. The process is nonlinear, so the efficiency scales with the light intensity. The special case is when both incident waves have the same frequency. This is the second harmonic generation. And many applications include frequency conversion for imaging and amplification. For example, laser pointers use SHG to generate their green light. However, most of these applications use crystals, nonlinear crystals that might be expensive and quite bulky. So the interest is in having nonlinear metasurfaces. These metasurfaces are as thin as the nanoresonators themselves, which would be on the order of nanometers. The focus is on achieving high efficiencies. This is already a challenge because metasurfaces are usually thousands of times thinner than a crystal used in existing nonlinear applications. And the way to do this is that we seek resonances where the light can be concentrated. Some metasurfaces that demonstrate non-linear behaviors have basically been demonstrated in the last couple of years with different possible materials, including lithium niobate on the left and semiconductor materials like gallium arsenide. In particular, there has been very few demonstrations of metasurfaces for SFG, which is much more tricky to accomplish. What we really need is resonances at different wavelengths. The efficiencies that people typically encounter for unpatterned thin films are on the order of 10 to the minus 8 per 1 gigawatt centimeter squared input power, input intensity, sorry. But it's not just the resonances at particular wavelengths, it's also how the electrical fields overlap. That's where the polarization density arises. So the question is how to overlap fields at both incident frequencies as well as, of course, having resonant behavior. The reason why resonant behavior is so important is because the light is concentrated at those particular modes. This will lead to higher intensities inside the material that we're interested in. Recently, there's this work from Rossio at Australian National University who demonstrated infrared upconverging in nonlinear metasurfaces, and this was one of the first demonstrations of SFG in experiment for metasurfaces. And you can see how the resonant behavior in the calculations is not so obvious. The resonance is present, of course, but not as strong as it is possible, right? And so how can we tailor particular metasurfaces to enhance this resonant behavior, as well as overlap incident fields? So that leads us to the challenge in optimization. This is something I've been working on during my PhD, which is to find methods in optimization in electromagnetism that can be used to better efficiently calculate certain figures of merits that I want. So the main principle is, let's say we have a domain and it is filled with material. How do we know where to put the material in order to scatter the field the way that we want to? What we can do is perhaps go through every possible discrete site. Each would be a small chunk of the domain, and simulate every permutation of whether there should be material there or not. Of course, this is way too laborious if your simulation domain is already huge. And of course, this number of discrete sites will increase your resolution, but further increase the time it takes. So we need a way to massively reduce simulations. What I mean by this is that if I change the location of one aspect of the domain being material or not, can we accurately say how the field will change? And of course, this could be a small part of the entire metasurface, or it could be a periodic part of the entire metasurface. the significance is that if we do this laborious on-off approach, this could be potentially 2 to the power of n simulations. Of course, that is not really feasible. So we're looking for a methodology where we can massively reduce the number of simulations. And I'm talking just 2 simulations here. We will know exactly how the gradient for the material is calculated with just one forward simulation and 1 adjoint simulation. And this is enabled by reciprocity of Maxwell's equations. And this has led to the development of topology optimization, which originated in structural mechanics. And the idea is to find optimal material distribution for a given purpose using shape derivatives. For example, this is the case for structural mechanics, where we want to most efficiently fill space. This has been developed over the last decade or 2 by several notable researchers in the field. And this has led to metasurface designs that are very unintuitive, however, perform extremely well. So Jonathan Fan first used topology optimization to design beam deflectors. And most recently, Rodriguez has used it to optimize nonlinear effects, and this is the second harmonic generation case. And the question for us is, can we apply this to some frequency generation, which is the more general second order nonlinear interaction? So our work has been in deriving a set of equations for some frequency generation topology optimized metasurfaces. And the complexity is that whenever we perturb materials, the electromagnetic resonances of all frequencies change simultaneously. The nonlinear interaction strength also changes, because if we don't have material, there is no nonlinear coupling at all. And finally, the emission of the SFG wave will be different. And these set of equations are quite complex. I won't explain them, but they do exist. And the basic idea is that you use these equations to simulate electromagnetic shapes and then use them to calculate your derivatives. So as an example, we have used it for the SHG case, which is just one subset of the general case. So we start this with an initial pattern, or it could be random. And then over the course of the optimization, the algorithm will generally try to increase the SHG efficiency. So the conversion efficiency achieved is about 6%, which is about 10 times 6 greater than on-pattern film. However, we're most interested in SFG, which is the general case for any 2 wavelengths to mix. The aim is obviously to have resonance at 2 very different wavelengths. And the efficiency that we just were about to achieve was about 10 to the minus 5. This is about 1,000 times weaker than SHG for the added difficulty in the first place, but still about 1,000 times stronger than on-pattern film. And you can clearly see that the optimization tends towards having a resonance at the selected wavelengths. And the shaded regions are where the algorithm has the input wavelengths that we want, which is 1550 around and 1230. And the transmission dips indicate the resonant behavior and field enhancement. So we can see that the field insert is enhanced at both incident wavelengths. And then there is this standing wave structure inside. And the balance is between field concentration and material distribution at the two very different wavelengths. So in conclusion, we have derived a set of equations to efficiently calculate SFG shape derivatives. And then we have used these to generate metasurfaces with high efficiencies in the nonlinear regime. And in the future, we hope to explore further light-path interactions, and this could be applied to quantum systems with certain applications to spin parametric downconversion. And finally, there's this animation which shows how the optimization converges to the final shape, which is occurs over 100 iterations. So it's not that slow. Of course, the more iterations that you have, the longer it takes. Thank you very much.
Thank you. Thank you.